have you ever stopped and wondered how AI actually, well, thinks? You know, how it takes this giant mountain of data and somehow spits out a single, really smart prediction? Well, today we're going to peel back the curtain. We're going to look at 3 different ways a machine can learn to see the future. So, let's get into it.
I mean, think about it. This is happening around us all the time. Your inbox just magically knows what's junk. A website recommends the exact pair of shoes you were just thinking about. Your bank sends you an alert about a weird charge, like minutes after it happens. What is that? Is it some kind of mind reader? Is it just magic?
Well, the answer is, of course, no. It's not magic. It's actually something way more interesting. It is the power of machine learning. These are just algorithms that are really good at finding patterns and making what you might call educated guesses. And they've gone from being a simple convenience to being a huge part of our daily lives. So how do they actually pull it off? In this explainer, we are going to break down 3 classic models that are pretty much the bedrock of all predictive AI. We're going to meet a detective, we'll follow a flowchart, and we'll even consult an entire forest. Sound good? Let's get started.
All right, our first thinker is the detective. The technical name is Naive Bayes, but I want you to just picture a classic Sherlock Holmes type character. They don't have all the facts, not yet, but they are an absolute pro at weighing all the little clues to figure out the most likely story. And this approach, it's surprisingly powerful, used for everything from sorting documents to even medical diagnoses.
So, technically speaking, Naive Bayes is what we call a classification technique. It's all about using probability to figure out what bucket something belongs in. You know, is this email spam or not spam? Given these symptoms a patient has, which illness is the most probable? And it does all this just by calculating the odds based on stuff it's already seen in the past.
Now, the engine running this whole operation is something called Bayes' theorem. And I know, you see a formula like this, and it looks a little intimidating, but don't worry about the math here. The idea behind it is actually super intuitive. All it's really saying is this: as you get new evidence, you should update what you believe. That's it. It's just a formal way of learning from new information.
So, why do we call our detective naive? Well, because it makes a couple of huge, simplifying assumptions to make its job easier. First, it assumes all the clues are completely unrelated to each other. And second, it assumes every single clue is equally important. Now, in the real world, that's almost never true, right? But making these naive assumptions is exactly what makes the model so incredibly fast and often surprisingly good at its job.
All right, enough theory. Let's give our detective a real case to solve. We're going to forget about crime scenes for a minute. Today, we're headed to the golf course. The mission is simple. Based on the weather forecast, predict whether or not we're going to play golf.
Okay, so what's the first thing any good detective does? They review the old case files. Our model learns from data about 14 different days. For each day, it gathers clues. What was the weather like, the temperature, the humidity, was it windy? And most importantly, it knows whether people actually played golf on that day or not. These are the facts of the case.
Now, let's say we have a new day. Today's forecast is sunny, hot, normal humidity, and it's not windy. Okay, our detective gets to work. It starts calculating the probability that we'll play golf given those exact clues and compares it to the probability that we won't play. It's weighing the evidence for both sides of the story.
And the verdict is in. The probability of yes, we play is just a little bit higher than the probability for no, we don't. And because that yes number is bigger, our detective confidently makes the prediction, yes, we're playing golf today. Case closed.
Okay, on to our second thinker. If our detective was all about playing the odds, our next model is more like a super organized manager, one who makes every single decision using a flowchart. This is the decision tree. It's really popular in areas like banking, where you absolutely have to be able to explain why you made a certain decision.
A decision tree works pretty much exactly like it sounds. It builds a model that looks like, well, a tree or a flowchart. It starts with all of your data, and at every step, it asks a simple question that splits the data into smaller and smaller branches until it finally gets to an answer. It's kind of like playing a game of 20 questions.
And this is where it gets really cool, seeing the transformation. So on the left, you've got this messy, confusing table of tax data. But on the right, the algorithm has automatically turned all of that mess into this clean, logical flowchart that can predict if someone might cheat on their taxes. It literally takes chaos and creates order.
So let's run a test case through our flowchart. We've got a new person. Here's what we know. They did not get a refund, they're married, and they have a taxable income of $80,000. So we're going to feed this person's info into the top of our tree and just follow the path.
Okay, step 1. We start at the very top, at what's called the root of the tree. The first question is, was a refund filed? For our person, the answer is no, so that tells us which path to take. We follow the no branch down. We've arrived at our next decision point. This one asks about marital status. Well, our person is married, so we follow that branch. See what's happening? We're just answering a series of really simple questions.
And just like that, we're done. Our path ends right here at what's called a leaf node, and this leaf gives us our final prediction for this person. No, they will not cheat. It's a simple, clear, easy-to-follow path to get to a final answer.
Now, a single decision tree is awesome because it's so easy to understand, but let's be honest, it can sometimes be wrong. So what if we need something more accurate, more robust, especially for really high-stakes stuff like financial predictions or medical scans? Well, that brings us to our third and final thinker, the random forest.
The idea here is basically the wisdom of the crowd. You know, a single expert, or in our case, a single decision tree, might have its own biases or just make a mistake. But what if we made hundreds or even thousands of slightly different decision trees and then just had them all vote on the final answer?
This process has a kind of funny name. It's called bagging. But here's how it works. First, the algorithm just makes a whole bunch of smaller, random samples from the original data. Then, it builds a totally unique decision tree for each of those little samples. Now you have a whole forest of trees, and each one gets to make its own prediction. Finally, you just count the votes. Whichever answer gets the most votes becomes the final prediction. The really clever part is that the mistakes of any one individual tree just get canceled out by the rest of the crowd.
So, there you have it. 3 totally different ways that a machine can learn how to make predictions. We've met our probabilistic detective, our organized flowchart, and our democratic forest. Let's do a really quick recap to see what makes each one special. So first we had Naive Bayes, our detective. Its big strength is that it's just really simple and super fast. Then we have the decision tree, our flowchart. Its killer feature is that it's so easy for us humans to look at and understand exactly why it made the decision it did. And finally, you've got the random forest. This is our wisdom of the crowd, and its whole purpose is to be as accurate and reliable as possible.
From spotting credit card fraud to helping doctors make diagnoses to shaping the stock market, these models are all quietly working behind the scenes, shaping our world. They really aren't magic. They're just clever ways of using logic and probability. And now that you have a sense of how they think, it raises a pretty interesting question, doesn't it? What are we going to ask them to predict next?